Okay, so we would like to find the intervals of concavity of the function x over x squared plus 1. And let's recall that if the second derivative is positive on an interval I, it's important that I is an interval, then f is concave up, so I'm going to denote it with a smile on I. And if f double prime is less than 0 on I, then f is concave down on I. Okay, so this is what we're going to use, and therefore we should start by computing the second derivative of f. So we will have the first derivative is equal to 1 times x squared plus 1 minus x times 2x over x squared plus 1 squared. So this will give us 1 minus x squared over x squared plus 1 squared. Okay, let's do the second derivative. For the second derivative, we will have to be a little more careful. So the derivative of the top is negative 2x times the bottom, x squared plus 1 squared, minus the top times the derivative of the bottom. So for the derivative of the bottom, we will need to use the chain rule. So we will think of x squared plus 1 as y. So we're looking at y squared. And the derivative of y squared is 2y, meaning 2 times x squared plus 1. And we also multiply by the derivative of what we designate as y, which is 2x. Okay, so this quantity that we just multiplied by is the derivative of the denominator. And we divide by the square of the denominator, which will now give us the fourth power. So since we want to do different things with the second derivative, we should try to simplify it as much as possible. And for this reason, one might want to FOIL, but before we FOIL, we have a nice factorization, so we can pull out an x squared plus 1. So this will leave us a minus 2x times x squared plus 1 from the first summand. And then we can have a 1 minus x squared times 2 times 2x, that will be times 4x. And we divide by x squared plus 1 to the fourth power. So this will give us negative 2x times x squared plus 1 minus 4x times 1 minus x squared over x squared plus 1 to the third power. And now we can fold the top, and we will get minus 2x cubed minus 2x minus 4x plus 4x cubed over x squared plus 1 to the third power, which will give us 2x cubed minus 6x over x squared plus 1 to the third power. And since we will want to set this equal to 0, it might be a good idea to factorize it. So we can factor out the 2x, and we will have an x squared minus 3. And if we think of 3 as square root of 3 all squared, then this will be 2x times x minus square root of 3 times x plus square root of 3. Or we could use our quadratic formula. Either way, we find that if we set, oops, sorry about this, if we set f double prime of x equal to 0, then the numerator has to be 0. In general, whenever we have a fraction equal to 0, the numerator is equal to 0. And this means that x will be 0 square root of 3 or negative square root of 3. So what we're going to do now is what we called a concavity diagram. So we place the three points where the second derivative is 0 in their natural order. And we put two lines right here, one for the information for f double prime and one for f. And we know that f double prime is 0 at each of these points. And now we can look at the second derivative because we found a very nice expression for it right here. And we can see that if we that the denominator is always positive, so we don't even need to consider the denominator here. In other words, we can focus our attention on the numerator since we're interested in determining the sign. And if we plug in a huge number, let's say 1,000,000, then all the three factors on the numerator will be positive, which means that this will be positive here. And either we can keep plugging in numbers. So for example, between 0 and square root of 3, we can plug in 1. And if we plug in 1, we will see that 1 minus square root of 3 is a negative number. And that will give us a negative sign. But there's also this general remark that we can use that whenever we have a polynomial of degree 3 that has 3 distinct roots, then it changes sign across every root. So that's true for any degree, as long as we have the right amount of roots. So since this happens here, we know that our sign will follow an alternating pattern. And eventually that means that we will get the signs that we just put here. We would have obtained the same conclusion if we used testing points. So here we will put concave down, concave up, concave down, concave up. And these points are what are called inflection points. So we have 3 inflection points here. These are points where the type of concavity changes. And finally, we can present our answer in a nice way. And we can say that f is concave down on the interval from negative infinity to negative square root of 3. We can always make that closed for a continuous function. F is concave up on the interval from negative square root of 3 to 0, closed both ways. F is concave down. I'm sorry, did I say concave down before? I meant concave up for negative square root of 3 to 0. And from 0 to square root of 3, it's concave down. And finally, it's concave up on the interval from square root of 3 to infinity. And that's the comprehensive answer to this. And we're all set. Thanks for watching.